Let's do it. Your definitions for Boyle's law, you could have written constant temperature and then P1 V1 equals P2 V2. You could have written it that way. Or you could have said constant pressure, constant temperature, pressure and volume are inversely proportional. And then Charles' law, you put constant pressure, then you would have T1 over V1 equals T2 over V2. You could have written it that way, or you could have written out the words. Extrapolation, something about extending the data past what the experimental measurements were. Avogadro's law, equal volumes of gases at the same temperature and pressure have the same number of molecules or moles. Boiling point, it's where the liquid's vapor pressure is equal to the external air pressure. Okay, then we get to number 2, which is which of the following is not a valid measurement for pressure? That would be newtons over meters, N over M. Okay, because you would have to have, well, yeah, it doesn't give it squared at the bottom, and that's why. Number 3, the pressure of a gas didn't change, but its volume increased. What happened to the temperature? It increased. Therefore, it would increase the speed of the bumper cars. And so that's why the pressure would have stayed the same, because you'd have the same number of collisions. That's my bumper car picture, sorry. Number 4, which of the following temperature scales are absolute? That would be Kelvin. Number 5, a gas starts out with a volume of 516 mils at a pressure of 345 torr. If the volume decreases to 213 mils, but the temperature doesn't change, what is the new pressure? Okay, so here we are dealing with P1 V1 over T1 equals P2 V2 over T2, the combined gas law. And in this one, we are told that the temperature doesn't change, so we're not going to look at that. It starts out with a volume of, so this is the first volume, 516 mils, and a pressure of 345 torr. Its volume decreases to, sorry, we're looking for the new pressure. The volume decreases to 213 mils, and we want to know what is the new pressure. So you're going to divide this side by 213 mils, and then the mils will cancel. You'll be left with torr. You have 3 significant figures every place, so your answer will be, pressure 2 will be 836 torr. That's how you should have set it up. Okay? These are pretty straightforward compared to a lot of stuff you've already done. Let's see, number 6. A gas in a piston starts out with a volume of that, a temperature of that, and a pressure of that. If it ends with a volume of that and a temperature of that, what is its new pressure? Once again, we're going to use P1 V1 over T1 equals P2 V2 over T2. And so let's start plugging in. Starts with a volume of 156 mils and a temperature of 28.1 degrees Celsius. So we're going to go 273.15. That's going to be 10301. Okay, but we can't use that because we can only go to the tenths place. So it's going to be 301.3 because that 5 is going to roll it up, Kelvin. The pressure, so now we're doing P1 of 1.12 atmospheres. Okay, there's the first side. If it ends with a volume of 312 mils and a temperature of 87.2 degrees Celsius plus 273.15, and that's going to give us, let's see, 53.01, 1516, 360. We can only go to the tenths place. So this temperature is going to be 360.4 Kelvin. What is the new pressure? There we go. There, it's all laid out. So we end up with 56. I'm just going to check it. Yes, divided by that and that. Good. This is going to give us 3 significant figures. The new pressure is 0.670 atmospheres. Because the Kelvin will cancel, the mils will cancel, and you'll be left with the atmospheres. So that would be your answer. Number 7, fill in the blanks. A gas behaves more ideally at blank temperatures and blank pressures. He's looking for high temperatures and low pressures. Number 8, what is the pressure of 0.145 moles of nitrogen gas when it occupies 756 mils at that temperature? Okay, so here, moles are involved, so we're going to use the ideal gas law. And that is PV equals nRT. And here we are looking for, what is the pressure? So we're going to solve for pressure. RT over V. You know what, I'm just going to write it here. Boop. Okay, we're going to use the ideal gas law for that, which is PV equals nRT, but we're solving for pressure, so I'm going to divide both sides by V, and that's what we're going to use. It tells us here that the moles are 0.145 moles. We know that R is 0.0821 liters, atmospheres, moles, Kelvin. We're told that the temperature is, wow, it's in Kelvin already, 281.2 Kelvin. Not used to that. And the volume is, we need that in liters, and it's given in milliliters, so 0.756 liters. Otherwise, it won't cancel. We have 3 significant figures everywhere. The liter should cancel, the moles should cancel, the Kelvin should cancel, so we should be left with atmospheres, which is what we're looking for. And so that should give us 4.43 atmospheres. Once again, if your significant figures are off, just take off a point. If you got everything else right, that's great. If you didn't convert one of those things, it's going to mess everything up. So you really need to watch those conversions. And go ahead and grade it the way he's got it graded in here, unless you want to bring it to me and we'll figure it out. Let's see. So that was number 8. Number 9, the following reaction is done at STP. If the reaction produces 145 liters of methane, how many liters of hydrogen gas were consumed? Okay, so we have C plus 2H2 gas yields methane gas. And we are using 145 liters of this, and we want to know how many liters of this were necessary. Remember, you can treat them, you can just go back and forth like they were moles. So we're going to go 145 liters of methane times line, liters of methane to liters of hydrogen. There's 2 there, there's 1 here, and so it's just going to be 290 with 3 significant figures, liters of hydrogen gas. So I put the decimal there at the end to show that it's 3 significant figures, or you could have written it this way. If you didn't do that, if you just wrote 290, it is incorrect. You have to take off for the significant figures. So take off 1 point if you didn't do the significant figures correctly. Let's see. Number 10. The following reaction is done at STP. If 145 liters of oxygen are added to excess AS2, S3, I'm pretty sure it's astenine, but I'm not exactly sure. How many grams of that product will be made. Okay, so we have here dot, 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 plus we have oxygen. And then we have 2. Whoop, that's a solid, I'm so sorry. Those are the 2 players that we have. We have 145 liters of this, and we want to know how many grams of this. Now you know that the only way we can get from here to here is by using the mole bridge. So we're going to find the amount of moles of this, because we can't go from here to here as if we did in the last problem, because this is the gas, but this is a solid. So the only way we can get to the moles of this is through PV equals nRT. So N equals PV over RT. So we are told in this problem it's at STP, so the pressure is 1 atmosphere. The volume we are given as 145 liters, it's right there. R is 0.0821 liters atmospheres per mole Kelvin. And the temperature at STP is 0 degrees, so it's 0.273.15 Kelvin. And so when you do all that, we have 3 significant figures. So it's going to be 6.47 moles of oxygen. And once you have that, now, you know what, I'm going to go ahead and use that down here. 6.47 moles of oxygen. Now I can go from here to here. So moles of oxygen to moles of the product. That gets a 2, that gets a 9, and then we're going to go from the moles of that product to the grams of that product. 1 mole, and let's see, if you add that up, that's a heavy one. 197.84 grams. And so that's going to give you 285 grams of that product. So you had to figure out from this the moles, which we used PV equals nRT, the ideal gas law, to do that. Then we went across the mole bridge, which was here, and then we just went to the grams. And once again, I would check his grading to figure out partial credit. Number 11, in a mixture of 2 gases, the first gas has a mole fraction of 0.145. What is the mole fraction of the other gas? Well, we know that the total fraction is going to be 1.00, and so if the one gas is 0.145 plus whatever else we're looking for, the other partial pressures, so we'll put X here, this is going to be the mole fraction of the other gas. So you just subtract this from this, and X will end up equaling 0.855. That will be the mole fraction of the other gas. Because you know they have to add up to 100, which is 1. 100%, I should say, which is 1. And so you take that away from it, and you'll get what the mole fraction of the other gas is. 12. In a mixture of 2 noble gases, the partial pressure of krypton is 771 torr, while the partial pressure of argon is 987 torr. If there are a total of 1.78 moles of gas, how many moles of krypton and how many moles of argon are present? Okay, well remember that the mole fraction, let's say of krypton here, equals the partial pressure of krypton divided by the total pressure. Okay, and we have the partial pressure given to us of both gases. We have the partial pressure of krypton given to us at 771 torr, and we have the partial pressure of argon given to us at, let's see, 987 torr. So the total pressure, you just add those two up, and the total pressure is going to be 1,758 torr. There's your total pressure. Okay, and we are looking for how many moles? So let's get the mole fraction. And so to get krypton, we're going to go 771 torr divided by the total, which is 1758 torr. And so mole fraction for krypton is going to be 0.439. Now let's do it for the partial pressure for argon. And that's going to be 987 torr divided by 1758 torr. And that's going to give us 0.561. Now we have the partial pressures. And we are told what the total number of moles are. It's 1.78. So, I'm sorry, now we have the partial pressures. Now we have the mole fractions. And so we can multiply these mole fractions by the total number of moles to get how many moles there are. So we're told there's 1.78 total moles. And I'm going to do that again here, 1.78 total moles. And so that tells me that the moles of krypton is 0.781. And the moles of argon are 0.999. There you go. So you really had to know how to manipulate these guys to find your way through it. Okay. That was number 12. Let's go to number 13, which is on the back side of the test. Number 13, and the last two questions refer to this table. If the atmospheric pressure is 500 torr, give the approximate boiling point of water. Okay, so you look here and find on this chart 500 torr would be somewhere between 85 degrees Celsius and 90 degrees Celsius. And therefore, your answer would be between 85 and 90 degrees Celsius because that's where 500 torr would fall. And remember, the boiling point of water is when the vapor pressure equals the atmospheric pressure. That's how that works. Number 14, a chemist collects gas produced in a reaction over water. The pressure of what is collected is 0.988 atmospheres. What is the pressure in atmospheres of the reaction product if the experiment was done at 40 degrees Celsius? Okay, we have the total pressure is given to us as 0.988 atmospheres. We want to know the partial pressure of the reaction. And so we're told that the reaction happens over water. So we know that this is going to equal the partial pressure of what we're looking for, let's call it X, plus the partial pressure of water at that temperature. So let's find that because we're given the chart. It's at 40 degrees. So you go up here and look at 40 degrees Celsius and it gives us 55.3 torr. Oh. We're given 55.3 torr. But the reason I'm not putting it in there is because this is in atmospheres, isn't it? Right? So we have to convert. So I'm going to go times line torr atmospheres 1 atmosphere, 760 torr. And so that's going to give me 0.3 divided by 760, and 3 significant figures, 8 atmospheres. Okay, so now I can come up here and put in 0.0728 atmospheres. And so now I can go 0.988 minus 0.0728 atmospheres, and that gives me the partial pressure of the gas we're looking for, which is in 3 significant figures, 0.915 atmospheres. Okay. Oh, and that's what we were looking for. Okay, now, if you happen to do it in torr, then its pressure would be 696 torr, depending on if you went the other way and you converted that to torr and then you made your answer in torr. But either way, it's going to have 3 significant figures, and it's going to be one of those 2 answers, and this is why. Hey, we're done with that test. So get your folks to go ahead and initial that once it's graded, and then bring that in to show to us in your next class. And go ahead and follow the syllabus, and have a really blessed, Jesus-filled week, and I'll see you next week.